If tweaking boosts never sticks, it's time for learning to rank. We'll set up OpenSearch LTR and re-rank the top results with a tiny LambdaMART model so your signals cooperate instead of fighting. You've tuned BM25 and fiddled with field weights. The clicks and freshness still push different results. By the end of this video, you will know how to wire OpenSearch LTR, register simple features, and run a small LambdaMART re-ranker to make those signals work together. No deep math first, just clear steps you can follow with Python. I'm Professor Pi, teaching search and IR from basics to advanced with simple concepts-first Python that helps you solve bigger real-world problems. OpenSearch Learning to Rank with the LTR plugin and LambdaMART solves a common task. You start with a candidate list from a fast retrieval like BM25. Then you re-rank those candidates using a learned model that combines many signals. People reach for this when hand tuning fails or when click and business signals must be blended reliably. Success looks like more relevant top hits that match user behavior rather than a single text score. At a high level, LambdaMART is a boosted tree model tuned for ranking. It learns which features move items up or down in a list. That makes it good when features are a mix of text scores, numeric signals like clicks, and freshness. The trade-off is you need training labels or click aggregates. It is ideal for re-ranking a short candidate list, not for full index scoring. We will build a tiny end-to-end demo. We will ping a local OpenSearch node, create a tiny index with 2 documents, run a BM25 baseline query, register an LTR feature set combining BM25, clicks, and freshness, and finally upload a tiny LambdaMART model to re-rank with STLRT. This keeps concepts clear, so you see each step in isolation and how they connect. This snippet pings a local OpenSearch node to confirm connectivity. It shows the simple health check you run before doing anything else. The code creates a client pointed at your local cluster and calls a ping function, which returns a Boolean or raises an error. In practice, this tells you if OpenSearch is reachable and whether credentials or host settings need fixing. If ping fails, you stop and fix the node. If it succeeds, you proceed to index creation and feature registration. This keeps the rest of the tutorial focused on LTR rather than connection debugging. Next, we create a tiny index and add 2 documents. This snippet creates a small index and seeds 2 documents in OpenSearch. It demonstrates the minimal schema you need: a text field for retrieval and fields for click counts and timestamp for freshness. The code shows mapping creation, index creation, and 2 simple document inserts, so you have concrete records to query. With 2 documents, you can see how BM25 ranks them by text, and how additional features like clicks and recency could change the order. This tiny corpus keeps the example readable while illustrating the full pipeline from ingestion to re-ranking. Now we run a BM25 match query to see the baseline. This snippet runs a BM25 match query to show the baseline ranking. It issues a normal search against the text field using OpenSearch's standard match retrieval, so you can observe the default order based on term frequency and document length. The output shows the list of hits and their BM25 scores, which acts as the control for our experiment. Reading this baseline helps you spot where BM25 succeeds and where it misses signals like popularity or freshness. You will later compare these results with the LTR re-ranked results to evaluate improvement. Next, we register a feature set for LTR that mixes BM25, click signals, and recency. This snippet registers an OpenSearch LTR feature set combining BM25, clicks, and freshness. It demonstrates how to declare features so the LTR plugin can compute them at query time. One feature reads the BM25 score, another reads a click count field, and a third converts a timestamp into a freshness score. The code shows naming each feature and giving simple expressions or scripts for their values. Defining these features makes the input for a LambdaMART model explicit. You can later change how freshness is computed or normalize clicks, and that will materially change the learned ranking behavior. Finally, we upload a tiny LambdaMART model and call STR to rerank. This snippet uploads a tiny LambdaMART model to OpenSearch LTR and re-ranks with SLTR. It shows the model payload you register with the plugin, and then performs a search that asks OpenSearch to score the top candidates using the uploaded LambdaMART model. The model itself is trained externally on the feature set we registered, and then serialized into the expected format. This re-rank step replaces naive score combinations with a learned ordering, so BM25, clicks, and freshness act as a team. Because re-ranking usually happens on a short candidate list, the latency impact is small, while accuracy gains can be large. To map this tiny demo to a production flow, swap the two documents for your real catalog, collect click data and label relevance judgments, train LambdaMART on hundreds or thousands of queries and features, and then push the model to OpenSearch to re-rank the top candidates from your faster retrieval stage. Recap: learning to rank in OpenSearch uses a re-ranking model that combines many signals. Use it when you need clicks, freshness, and text relevance to cooperate. Caveat: you need training data and careful feature design to avoid overfitting. Next step: retrain the LambdaMART model while tuning BM25 parameters K1 and B. Or swap the freshness feature for a time decay variant and measure NDCG on held out queries. If short, practical IR helps, subscribe and watch the IR videos.